Applied mathematics bridges pure thought with real action. We use mathematical tools to solve practical problems. Think of it as math with a mission, seeking answers in our complex world. This discipline is about tangible results and understanding. Many fields rely heavily on its power, like science, engineering, and economics. Applied mathematics is deeply practical, developing solutions for everyday challenges. Applied mathematicians create models representing real systems. They use math to analyze these models, predicting outcomes and optimizing processes. The goal is always clear: improve, solve, understand. Unlike pure mathematics, which explores concepts for their own sake, applied mathematics is goal-oriented. Pure math builds the foundational language. Applied math uses this language to write stories about reality. Applied mathematics finds its elegance in utility and its power to change things. It helps us make better decisions and build more efficient systems. The scope of applied mathematics is incredibly broad, touching almost every aspect of modern life. From designing faster computer chips to predicting weather patterns, it helps. It manages financial risks and is vital in medical imaging. It plays a role in logistics and supply chains. Where there is complexity and a need for optimal solutions, applied mathematics illuminates the path forward. It truly is a versatile and powerful toolkit for innovation. Analytics focuses on improving decision-making using scientific and mathematical methods, or aims to make systems more efficient and effective. Think of complex organizations needing guidance, or provides that analytical support. It helps find the best possible ways to operate. This field emerged from wartime challenges and now solves problems in many industries. The core of analytics is problem-solving. Analytics tackles intricate operational puzzles like optimizing factory production, reducing hospital wait times, and improving delivery routes. Professionals in this field use a structured approach, defining the problem, gathering data, and building models to find solutions. Or is often described as the science of better, capturing its essence perfectly. It is about finding the best solution, maximizing something good or minimizing something undesirable, or provides tools for informed, data-driven decisions rather than just intuition. Many industries benefit greatly from analytics, including logistics, transportation, airlines, manufacturing, healthcare, and financial services. Anywhere complex decisions involve limited resources, Oregon offers valuable insights and powerful methods for improvement. It is a key driver of innovation. Applied mathematics forms the backbone of analytics, or practitioners use mathematical techniques to model and analyze complex systems. Without applied mathematics, Oregon would lack its rigor and power to find optimal solutions. Mathematics provides the language and engine for OR's analysis. Consider the types of problems or tackles, often involving many variables, constraints, and uncertainties. Human intuition alone cannot manage such complexity. Applied mathematics offers the necessary tools to abstract and translate problems into mathematical forms. This process brings clarity to complex situations. Specific mathematical fields are essential optimization theory, probability theory, linear algebra, and calculus. These are practical tools used daily by analysts worldwide. They solve real operational challenges across many sectors. This partnership empowers organizations to achieve more, improving efficiency, reducing waste, and enhancing productivity. It leads to better resource utilization, cost savings, improved services, and a stronger competitive advantage. The synergy between these two fields drives innovation and operational excellence. Several key mathematical disciplines are pillars for analytics. Algebra provides tools for representing relationships with variables and equations. Linear algebra, a subfield, is vital for handling large data sets and solving systems of linear equations. Calculus, the study of continuous change, helps find rates of change and accumulate quantities. Probability theory is central to analytics, providing a framework to quantify and manage uncertainty. Optimization is perhaps the most iconic tool in the OR toolkit, focusing on finding the best solution from a set of feasible solutions. Linear programming, nonlinear programming, and integer programming are common techniques. These methods have transformed industries by finding optimal ways to operate complex systems effectively. Mathematical modeling is the heart of applied mathematics and analytics. It creates a mathematical representation that captures a real-world system or problem. The model uses mathematical language, simplifying reality to its essential components. A good model helps us understand and predict system behavior. Models allow organizations to test scenarios without real-world disruption. This experimentation is low-cost and low-risk, identifying bottlenecks and revealing areas for improvement. Mathematical models provide a clear, objective basis for decisions. Instead of relying on guesses, managers use data and analytical insights from models. This leads to more consistent outcomes and justifiable decisions. For example, a supply chain model can show the cheapest way to distribute goods. A staffing model can determine optimal employee schedules. These models bring precision to complex operational choices and enhance management quality. Mathematical modeling drives operational efficiency by enabling informed choices. It helps optimize resource allocation, reduces waste, cuts costs, and improves throughput and service levels. Companies that embrace modeling gain an edge, becoming more agile and responsive. Optimization is a central theme in analytics. It is the art and science of making the best possible choices. Optimization helps find the one option that truly excels, whether maximizing profits, minimizing waste, or achieving the quickest delivery route. This pursuit of the optimal drives many OR studies. Every optimization problem has an objective function, decision variables, and constraints. The objective function describes what we want to maximize or minimize. Decision variables represent the choices we can make. Constraints are the rules or limitations we must adhere to. Optimization provides a systematic way to achieve efficient resource allocation. It moves decision-making from intuition to a rigorous, data-driven approach. It strives to find the provably best solution, leading to significant improvements in performance and competitive advantage. While formal optimization techniques are mathematical, the underlying idea is intuitive. We all try to optimize things in our daily lives, like finding the shortest route to work. Analytics formalizes this natural human desire with powerful mathematical tools. This allows for tackling incredibly complex problems with many variables and constraints. Linear programming, or LP, is a widely used optimization technique. It determines the best way to achieve an objective, like maximizing profit or minimizing cost. The crucial characteristic of LP is that all mathematical relationships involved are linear. This linearity simplifies the problem, making it solvable through established algorithms. For LP models to be applicable, certain assumptions must hold true: proportionality, additivity, divisibility, and certainty. Understanding these assumptions is vital for correctly applying LP. The constraints in an LP problem define a feasible region, representing all possible combinations of decision variables that satisfy the limitations. A fundamental theorem in LP states that if an optimal solution exists, it must occur at one of the corner points of this feasible region. Algorithms like the simplex method explore these corner points to find the best solution efficiently. Consider a bakery producing two types of cakes with limited ingredients and different profits. The bakery owner wants to decide how many of each cake to bake to maximize total profit. This scenario can be formulated as an LP problem, with decision variables, an objective function, and constraints. While linear programming is powerful, not all real-world problems fit its linear assumptions. Quadratic programming, or QP, comes into play for these cases. In a QP problem, the constraints are linear, but the objective function is quadratic. This allows modeling a broader range of situations more accurately. Many important relationships in business and engineering are inherently nonlinear. For instance, in finance, the risk of an investment portfolio is often measured by variance, a quadratic function. In production, the cost per unit might decrease with volume due to economies of scale, then increase again, forming a U-shaped cost curve. LP cannot capture these curved relationships. QP can. In LP, the optimal solution is always at a corner point of the feasible region. With QP, the optimal solution can occur anywhere within the feasible region or on its boundaries. Solving QP problems is generally more computationally intensive than LP problems. Consider portfolio optimization. An investor wants to allocate funds among various stocks to minimize risk for a desired return. The expected return is a linear function, but the risk is quadratic due to covariances between stock returns. QP provides the framework to find the optimal allocation, balancing risk and return. Section 4. Optimization in action reducing supply chain costs. Let us explore a practical application of optimization through a case study focused on supply chain cost reduction. Imagine a large manufacturing company, Global Goods Inc., that produces items in several factories. These goods are then stored in regional warehouses before being shipped to numerous retail customers. The company faces significant annual expenses related to transportation, inventory holding, and factory operations. The management team believes these costs are too high and seeks a systematic way to identify potential savings across their complex network of facilities. Global Goods Inc. decides to use an optimization model, likely a linear programming model or a mixed integer programming model, which includes discrete choices, to analyze its supply chain. The first step is to define the decision variables. These would include quantities like the amount of each product to manufacture at each factory. They also include how much of each product to ship from each factory to each warehouse, and from each warehouse to each customer. The primary objective function is clearly defined to minimize the total sum of all relevant supply chain costs. This includes production costs, transportation costs between all points, and inventory holding costs at warehouses. Next, the team at Global Goods Inc. meticulously defines the constraints of their supply chain. Factory constraints include limits on production capacity for each product line. Warehouse constraints involve maximum storage space and throughput capacity. Customer demand constraints ensure that all orders are met on time and in full. There might also be constraints on specific shipping lanes, perhaps due to limited carrier availability or transport mode capacities. All these real-world limitations are translated into mathematical inequalities or equations, forming a large-scale optimization model which can involve thousands or even millions of variables and constraints. Once the model is built and solved using specialized optimization software, the results provide actionable insights. The model might reveal that shifting production of certain items to different factories could lower overall costs. It could suggest reconfiguring warehouse territories to serve customers more efficiently. It might identify opportunities to consolidate shipments, reducing transportation expenses. By implementing the recommendations from the optimization model, Global Goods Inc. could potentially achieve substantial cost reductions, perhaps in the range of 5 to 15% of their total supply chain expenditure. This also often leads to improved service levels and better resource utilization, demonstrating the tangible value of analytics. Section 5. Broadening the horizon, diverse applications of optimization. Optimization techniques extend far beyond supply chain management. They help make the best decisions under constraints. Wherever resources are limited, optimization offers invaluable insights. It impacts various industries globally. In finance, it balances risk and return. In manufacturing, it aids in production scheduling. In healthcare, it schedules staff and allocates resources. Optimization is a cornerstone of analytics. Embracing uncertainty, the role of probability in analytics. The world of operations is rarely perfectly predictable. Many real-world systems are full of surprises. Customer demand can fluctuate wildly. Machines can break down without prior warning. Delivery times can vary due to traffic or weather. These elements of chance are what we call uncertainty. Analytics uses probability to manage this uncertainty. Ignoring uncertainty can lead to failed plans. Probability helps quantify and manage uncertainty. It provides a language for discussing uncertainty. Probability quantifies the likelihood of events. Think of it as a precise way to talk about chance. Basic concepts include events and sample spaces. Probability is a number between 0 and 1. It represents the likelihood of an event. Assigning probabilities helps make informed decisions. This is crucial for decision-making in uncertain environments. Knowing machine failure probabilities aids maintenance planning. Understanding demand probabilities helps set inventory levels. We can calculate expected values using probabilities. For example, expected profit from a new venture. It allows for rigorous risk assessment. Analytics uses probability to create realistic models. Statistical modeling builds on probability theory. probability deals with theoretical chance. Statistics uses data. Data informs probabilistic models. Combining theory and data allows sophisticated approaches. These approaches incorporate uncertainty into decision-making, leading to more resilient and effective strategies. Peering into the future, understanding Markov chains. Markov chains are probabilistic models representing systems transitioning between states over time. They help predict future states based on the current state, not the history. This simplification is powerful for predictive modeling. Applications include weather forecasting, customer behavior, and machinery reliability. Simulating reality, the power of Monte Carlo methods. Monte Carlo simulation uses repeated random sampling to generate numerical approximations. It's powerful for complex systems with many interacting uncertain variables. Instead of solving equations, we simulate the process many times. This helps in risk assessment and managing uncertainty effectively. Applications are widespread, from project management to financial engineering. Let's consider a very common and practical analytics problem: inventory management. Almost every company that sells physical products faces the challenge of deciding how much stock to keep on hand. Holding too much inventory ties up capital, incurs storage costs, and risks items becoming obsolete or spoiling. However, holding too little inventory can lead to stockouts, resulting in lost sales, frustrated customers, and emergency replenishment costs. The core difficulty in striking this balance often stems from the unpredictable nature of customer demand and the variable time it takes to receive new stock from suppliers, known as lead time. This is where probability models become indispensable. To make intelligent inventory decisions, we first need to characterize the uncertainty. Customer demand for a particular product over a given period, say a day or a week, is rarely constant. It often fluctuates randomly. Analysts use historical sales data to fit a probability distribution, perhaps a Poisson distribution for items with low average demand, or a normal distribution for items with higher demand, to model this variability. Similarly, the lead time for an order from a supplier can also be uncertain due to production delays or transportation issues, and this too can be represented by a probability distribution. With these probabilistic models for demand and lead time, we can then address key inventory decisions more scientifically. A critical question is, how much safety stock should be maintained? Safety stock is extra inventory held to buffer against unexpectedly high demand during the lead time or an unexpectedly long lead time. Probabilistic models allow us to calculate the level of safety stock needed to achieve a desired customer service level, such as a 95% probability of not stocking out while waiting for an order to arrive. Another crucial decision is the reorder point. At what inventory level should a new order be placed? This too depends critically on the probabilistic forecasts of demand during lead time. The benefits of applying such probability models to optimize inventory are substantial and well documented. By systematically accounting for uncertainty, companies can significantly reduce the occurrences of costly stockouts, thereby improving customer satisfaction and preventing lost revenue. Simultaneously, they can often lower their overall average inventory levels, which frees up working capital, reduces warehousing costs, and minimizes losses from products becoming outdated or perishing. This leads to a more efficient, responsive, and ultimately more profitable supply chain. It is a classic example of how applied mathematics, through probability, delivers tangible business value in operations. While probability theory lays the crucial groundwork for understanding randomness, statistical modeling takes these concepts further by using data to build and test models of real-world phenomena. In analytics, the toolkit extends far beyond basic probability calculations, Markov chains, or Monte Carlo simulations. Advanced methods enable nuanced comprehension of operational dynamics. Regression models quantify relationships between variables, aiding in predictions and decision-making. Queuing theory uses probabilistic models to design efficient service operations. Machine learning techniques tackle complex pattern recognition and prediction tasks. Matrices are powerful tools in applied mathematics. Think of a matrix as a rectangular grid of numbers. These numbers are arranged in rows and columns. This structure organizes vast data compactly. In analytics, matrices represent complex information systematically. They reveal patterns and relationships, making problems approachable. Matrices are essential in solving systems of linear equations. They help allocate resources and meet specifications. Linear algebra provides the rules for working with matrices. It is a fundamental toolkit for analytics. Matrices help conceptualize and structure complex problems. They represent networks and transformations, creating a visual and logical framework. This framework is the first step towards optimal solutions. Matrices underpin much of modern analytics. Section 2. Solving the puzzle's core linear algebra techniques. Solving systems of linear equations is central to analytics. These systems often take the form of a matrix equation. Ax equals b. A is a matrix of coefficients. X is the vector of unknowns, and b is the vector of constants. Gaussian elimination is a fundamental method to solve these equations. It transforms the system into a simpler one to find solutions. Matrix operations like addition, subtraction, and multiplication are essential. These operations build the foundation for advanced analyses. Matrix inversion is another powerful concept, solving Ax equals b directly. However, Gaussian elimination is often more practical for large systems. Section 3. When exact answers hide. The necessity of numerical methods. Not all challenges in analytics yield to exact solutions. Some problems are too large with thousands of variables. Others involve non-linear relationships. Perfect solutions can be impractical. Numerical methods are essential. They find approximate solutions through algorithms. Iteration refines guesses step by step. Each step aims to get closer to the true solution. Iterations continue until the solution is good enough. Numerical methods balance accuracy and effort. They are crucial for solving complex, large-scale problems. Section 4. Case Study, Matrix Power in Logistics and Transportation. Speedy Deliveries optimizes its logistics using matrices to minimize costs and meet demands. Matrices represent shipping costs, supply, and demand. Linear programming finds the optimal shipping plan. This reduces expenses and improves fleet utilization. Matrix models enable quick what-if scenario analysis. Adapt and re-optimize for dynamic logistics planning. Computational methods, rooted in linear algebra and numerical techniques, have transformed analytics. These methods tackle operational challenges of astonishing scale and complexity. They have expanded OR's impact across all industries. The synergy between mathematical methods and computing technology is powerful. Integrating these methods with AI and machine learning opens new frontiers. The world of data analytics is entering a fascinating new chapter. Artificial intelligence is merging with traditional mathematical optimization. This combination unlocks new levels of problem-solving power. AI excels at finding patterns in vast data. It learns and adapts. Optimization finds the best solutions within constraints. Together, they tackle complex problems. This synergy creates exciting possibilities. AI is revolutionizing analytics by tackling complex decision-making problems with its adaptive learning capabilities. It excels in dynamic environments with incomplete information, offering new solutions where traditional models struggle. AI's ability to learn and adapt makes it ideal for messy, less structured scenarios. It can optimize complex systems like city transportation networks and personalize e-commerce recommendations. AI's role in healthcare and smart factories highlights its potential for autonomous decision-making and system optimization. Section 3. The Moral Matrix, Ethics in Data-Driven Analytics. As mathematical modeling becomes increasingly data-driven, ethical considerations take on a new level of importance. The models we build in analytics have real-world consequences. They can influence who gets a loan, how medical resources are allocated, or even how policing efforts are directed. Therefore, it is crucial for analytics to think deeply about the ethical implications of their work. The pursuit of efficiency must be balanced with fairness, transparency, and accountability. One major ethical concern is bias in data and algorithms. AI models learn from the data they are fed. If this data reflects societal biases, the models will perpetuate these biases. For example, an algorithm trained on biased hiring data might disadvantage certain groups. An optimization model could inadvertently direct resources away from underserved communities. Recognizing and mitigating these biases is critical for equitable outcomes. Transparency and explainability are also key ethical challenges. Many advanced AI models operate as black boxes. It can be difficult to understand why they make a particular decision. This lack of transparency can be problematic, especially when decisions impact lives. If a model denies someone a critical service, they have a right to understand the reasoning. Analysts are developing explainable AI, XAI, techniques to provide insights into decision-making processes. Finally, considerations of privacy and data security are paramount. Mathematical models often rely on sensitive personal information. Ensuring this data is collected, stored, and used ethically is essential. This includes obtaining proper consent, anonymizing data, and implementing robust safeguards. Analysts must adhere to legal regulations and ethical best practices. The goal is to harness data for improvement without compromising individual rights or societal values. Section 4. Charting New Waters, Emerging Mathematical Paradigms in OR. The field of applied mathematics and analytics is constantly evolving. New mathematical ideas and techniques are continually emerging to solve complex operational problems. Core disciplines like linear programming remain fundamental, but new paradigms are pushing OR's boundaries. These trends promise powerful tools for global challenges. Section 5. Operations on a global stage. The future of applied mathematics. The scope of analytics is increasingly global. Applied mathematics provides the essential toolkit for addressing global-scale operational problems. Future advancements will drive efficiency, sustainability, and resilience in operations affecting billions. Distributed optimization allows separate entities to coordinate actions for a global optimum. Sustainability and environmental considerations are driving new applications in global OR. Mathematical modeling helps balance economic objectives with ecological responsibility. Enhancing global resilience to disruptions is a critical area of ongoing research. This course has taken us on a significant journey. We explored the vital role of applied mathematics in analytics. We began by defining applied mathematics itself. It is math with a clear, practical purpose. It seeks to solve real-world problems effectively. We also decoded analytics. It is the science of making better decisions. It aims for efficiency and effectiveness in complex systems. The partnership between these two fields is truly indispensable. Applied mathematics provides the tools and the rigor. We then surveyed the key mathematical disciplines. Algebra helps us structure problems with variables and equations. Calculus allows us to understand rates of change and accumulation. Probability theory gives us a framework to manage uncertainty. Optimization techniques guide us to the best possible outcomes. These are not just abstract concepts. They are the foundational pillars upon which OR builds its powerful solutions. Understanding these pillars is crucial for anyone in the field. They form the language of operational improvement. A central theme throughout our exploration has been mathematical modeling. This is the process of creating simplified representations of reality. These models use mathematical language to capture essential features. We saw how models allow for analysis and prediction. They enable experimentation without real-world risk. The importance of such modeling for achieving operational efficiency cannot be overstated. It transforms complex challenges into manageable forms. It provides a clear basis for making informed, strategic decisions. Ultimately, applied mathematics empowers analytics to deliver tangible results. It helps organizations improve processes. It aids in reducing waste and cutting down on costs. It enhances productivity and resource utilization across various sectors. The core message is clear. Mathematics is not just for theorists. It is a practical, powerful toolkit for anyone looking to make operations smarter, faster, and better. This understanding is the first step towards mastering its application in the field of OR. Section 2. The enduring power, optimization, probability, and insight. We delved deeply into optimization techniques. These methods are at the heart of finding the best solutions. Linear programming showed us how to tackle problems. These problems involve linear relationships and constraints. We saw its power in scenarios like resource allocation. Quadratic programming extended this capability. It allowed for non-linear objectives, crucial in areas like finance. The supply chain case study demonstrated this vividly. Optimization models helped identify significant cost reductions. They streamlined complex logistical operations with precision. The enduring relevance of these optimization tools is undeniable. In a world of limited resources, making optimal choices is paramount. Businesses continually seek ways to improve their bottom line. They want to enhance customer satisfaction efficiently. Optimization provides a systematic, data-driven approach to these goals. It moves beyond intuition to mathematically sound strategies. The ability to formulate a problem and find its optimal solution is a core skill. It remains a highly valued competence for analysts dealing with diverse challenges. Alongside optimization, we explored probability and statistical modeling. These tools are essential for embracing and managing uncertainty. The real world is seldom perfectly predictable. Markov chains offered a way to model systems. These systems transition between states over time. They help in understanding long-term behavior. Monte Carlo simulation provided a powerful method. It uses random sampling to assess risk and analyze complex scenarios. It allows us to see a range of possible outcomes, not just one single estimate. The inventory management case study highlighted probability's practical impact. By modeling uncertain demand and lead times, we can optimize stock levels. This reduces both costly stockouts and excessive holding expenses. Such probabilistic thinking is vital. It leads to more robust and resilient operational plans. It ensures that strategies can withstand the inherent variability of the real world. The ability to quantify uncertainty and incorporate it into decision-making processes is a hallmark of effective analytics and a testament to applied mathematics. Section 3. The computational backbone, matrices, algorithms, and modern solutions. Our journey continued into the realm of matrix and computational methods. Matrices serve as the unseen organizers in analytics. They provide a structured way to represent large amounts of data. They are essential for handling systems of linear equations. These systems often arise from complex operational problems. Linear algebra, the study of matrices and vectors, provides the rules. It offers the techniques for manipulating these structures. This is fundamental for modeling many real-world scenarios efficiently. We examined core linear algebra techniques. Methods like Gaussian elimination help solve these systems of equations. They determine if unique solutions exist or if problems are ill-defined. Basic matrix operations, such as addition and multiplication, are building blocks. They help in constructing and analyzing models. The concept of a matrix inverse offers another path to solutions. These tools are not just theoretical, they are embedded in the software that operations researchers use daily. They make complex calculations feasible and manageable. The necessity of numerical methods became clear. Not all problems yield exact analytical solutions quickly. Some are too large or involve nonlinearities. Numerical methods use iterative algorithms. They start with a guess and progressively refine it. This approach provides approximate but highly useful solutions. It balances accuracy with computational feasibility. The simplex method for linear programming is an example. Gradient descent for nonlinear problems is another. These algorithms are the workhorses of modern OR. The case study on logistics and transportation showcased this power. Matrix-based models helped optimize shipping routes and schedules. This led to significant cost savings and improved efficiency. Such computational methods form the algorithmic edge. They allow OR to tackle problems of immense scale. They transform raw data and mathematical models into actionable insights. The synergy between mathematical theory and computational power is what drives so many successes in analytics today, enabling sophisticated analysis of intricate systems. Section 4, Navigating the Horizon: AI, Ethics, and Evolving Frontiers. We then shifted our gaze towards the future of applied mathematics and analytics. The convergence of artificial intelligence and traditional optimization is heralding a new era. AI, especially machine learning, can enhance optimization models. It provides better input data through improved forecasting. It can also assist in solving extremely complex problems. Reinforcement learning, for example, can find effective strategies in dynamic environments. This integration is paving the way for more adaptive and intelligent decision-making systems. AI's expanding role allows us to address problems of unprecedented complexity. It helps in situations with high ambiguity or incomplete information. From optimizing citywide transportation networks to personalizing customer experiences, AI offers new capabilities. It can enable more autonomous decision-making in operational settings. Smart factories and self-optimizing supply chains are becoming realities. This intelligent automation promises significant gains. It can boost productivity and responsiveness. However, this power brings with it important considerations. The ethical dimension of data-driven analytics is crucial. Models can perpetuate biases present in historical data. This can lead to unfair or discriminatory outcomes. Transparency and explainability of complex models, especially AI, are vital. We must strive to understand why models make certain decisions. Privacy and data security also demand careful attention. The responsible use of data is paramount to maintaining public trust. Operations researchers have a duty to ensure their work is fair, transparent, and benefits society. Finally, we touched upon emerging mathematical paradigms. Topological data analysis offers new ways to find patterns in complex data sets. Network science provides tools to understand interconnected systems. Advanced uncertainty quantification aims for more robust decision-making. These evolving frontiers show that applied mathematics is a living field. It constantly adapts to meet new challenges. These new tools will be vital for tackling global-scale operations. They will help in areas like sustainability and global resilience, pushing the boundaries of what OR can achieve. Section 5. The Unfolding Narrative: Lifelong Learning in a Dynamic Field. In conclusion, the journey through applied mathematics and analytics reveals a field of immense power and enduring relevance. From the foundational principles of algebra and calculus to the sophisticated techniques of optimization, probability, and computational methods, mathematics provides the bedrock for transforming complex operational challenges into opportunities for improvement and innovation. The ability to model, analyze, and optimize is not merely an academic skill. It is a vital competency that drives efficiency, reduces costs, and enhances decision-making across countless industries globally. The significance of applied mathematics in this domain is not static. It continues to grow and evolve. As we have seen, emerging trends like the integration of artificial intelligence, the increasing focus on ethical considerations, and the development of new mathematical paradigms are constantly reshaping the landscape. These advancements open up new possibilities for tackling problems of even greater scale and complexity, from optimizing global supply chains to addressing pressing societal issues such as sustainability and healthcare delivery. The tools are becoming more powerful, and the scope of their application is ever expanding. This dynamic nature underscores a critical point: the importance of continuing education. For analytics, analysts, and professionals who rely on these mathematical modeling skills, learning cannot be a one-time event. Staying updated with emerging trends, new algorithms, innovative software tools, and evolving best practices is absolutely essential. The field moves quickly, and those who commit to lifelong learning will be best equipped to harness the full potential of applied mathematics to solve the problems of tomorrow effectively and responsibly. Therefore, let this course serve not as an endpoint, but as a stepping stone. We encourage you to continue exploring, to deepen your understanding, and to actively engage with the vibrant community of applied mathematicians and analytics. The narrative of applied mathematics and analytics is continually unfolding, and by staying curious, adaptable, and committed to learning, you can play an active role in writing its next exciting chapters, contributing to a future where decisions are smarter, systems are more efficient, and operations truly achieve their full potential.